The promise of quantum computing once felt like the dawn of a new scientific era. Machines capable of solving problems in minutes that would take classical supercomputers thousands of years. A future where encryption becomes obsolete, new medicines are discovered overnight, and the deepest mysteries of physics finally begin to unfold. At the center of this revolution stood one machine, Google's Sycamore quantum processor. When Sycamore first demonstrated quantum supremacy, the world celebrated. For the first time, a quantum computer completed a calculation that would have been practically impossible for traditional machines. Researchers believed they were standing at the edge of a technological explosion that could redefine everything from artificial intelligence to cosmology. But behind the headlines and celebration, a quieter story began to unfold. Inside the labs, the chip was being pushed further. Researchers weren't just testing speed anymore. They wanted to explore what quantum systems could reveal about the fabric of reality itself. Quantum computers don't work like ordinary machines. Instead of bits, they use qubits, particles that can exist in multiple states at once. This allows them to explore countless possibilities simultaneously. In theory, this makes them perfect tools for simulating the universe at its most fundamental level. At first, everything behaved exactly as expected. Experiments matched theoretical predictions. Calculations lined up with quantum models. The machine performed beautifully. And then the anomalies began. It started with strange outputs buried deep inside routine experiments. Small irregularities that looked like noise. Minor glitches that researchers assumed were hardware errors or software bugs. That happens often in experimental technology, especially something as delicate as a quantum processor. But these irregularities didn't disappear. They multiplied. The chip began producing data that didn't match the parameters of the experiments it was running. Streams of numbers appeared where none were expected. Patterns surfaced that didn't correspond to any programmed calculation. At first, the team assumed the system was misreading qubits or experiencing interference from the environment. So they ran diagnostics. They checked the hardware. They reviewed the code. Everything came back clean. The machine was functioning perfectly. Which meant the data shouldn't exist. As researchers dug deeper, the anomalies became harder to dismiss. The unexpected outputs weren't random. They were structured, repeating, patterned. The kind of patterns scientists are trained to recognize as meaningful. Advanced analysis software was brought in to examine the data streams. What it found raised even more questions. Certain sequences appeared to follow mathematical symmetries that had never been programmed into the system. Structures emerged that didn't resemble noise, errors, or known quantum behavior. The machine was generating information that no one had asked for. The atmosphere in the lab shifted from excitement to unease. The experiments continued. Researchers tried to isolate the anomaly, to reproduce it under controlled conditions. And that's when things became even stranger. The unexplained outputs began appearing more frequently during simulations designed to model complex physical systems, especially experiments attempting to simulate the early universe and higher dimensional physics. Some of the results suggested mathematical structures that didn't fit existing models of spacetime. Calculations hinted at geometries that couldn't be visualized in 3 dimensions. Equations appeared that researchers couldn't trace back to any input or algorithm. It was as if the machine had stepped beyond the boundaries of its instructions. Inside the research teams, debates intensified. Some believed the anomalies were simply the result of unknown quantum behavior. Others suspected undiscovered errors in the experimental setup. But a growing number of scientists quietly admitted a more unsettling possibility. What if the machine wasn't malfunctioning? What if it was discovering? Quantum systems interact with reality at its most fundamental level. They don't just process information, they explore possibilities embedded in the laws of physics themselves. If any machine could stumble upon unexpected truths, it would be a quantum computer. The deeper the team investigated, the less certain they became. Then, suddenly, the project changed direction. Access to certain datasets became restricted. Experiments were paused. Internal discussions grew quieter. Researchers who had been focused on the anomalies were reassigned to different tasks. Official communication slowed to a trickle. And eventually, the experiment stopped. No dramatic announcement. No public explanation. Just silence. From the outside, it looked like the natural ebb and flow of research priorities. Large technology projects change direction all the time. Funding shifts. Teams reorganize. Experiments pause. But inside scientific circles, whispers began to spread. What had the machine actually found? Quantum computing remains one of the most unpredictable frontiers in modern science. It operates in a realm where probability replaces certainty, where particles can exist in multiple states at once, and where observation itself changes reality. Even today, scientists admit that we do not fully understand the quantum world